Here at Warwick Control Technologies, we have some great value kits to help troubleshoot the NMEA2000 CAN bus. In this video, we shall showcase the kits, give a basic overview of Controller Area Network, or CAN, and then explain how these technologies can be used to help identify faults on NMEA2000 networks. So let's run through what we shall cover in today's presentation. So we shall break down the Warwick Control NMEA2000 products and services, so what the product or service contains or includes, introduce the great value kits for NMEA2000 CAN bus troubleshooting and how they can help identify network faults, show the new N2K Picoscope Kit and how not all NMEA2000 devices are the same with CAN electrical signal analysis, show how to simulate NMEA2000 devices with the X-Analyzer 3 software, then show the fault injection board, a handy tool for checking bus off recovery. Now we shall give a brief overview of all the NMEA2000 products and services we provide. At Warwick Control, we provide a range of NMEA2000's products and services, from the NMEA2000 CAN bus analysis tools, for the electrical signals with the Picoscope, and then the data contained within these messages and signals with X-Analyzer 3 and a Cavasa interface, through to a combined NMEA2000 and J1939 protocol stack kit to speed up developing a device, to then offering NMEA2000 testing and certification of a device with technical feedback on any failures. So now let's talk about the products for troubleshooting. We have three products we would like to showcase today that can help troubleshoot faults. Firstly, our flagship software, X-Analyzer 3 Professional. This includes such features as decoding NMEA2000 signals like water speed, wind direction, using the embedded NMEA2000 signals database. X-Analyzer 3 can plot the movement of these signals on a scope and display the signal within a panel or gauge. A new X-Analyzer 3 feature is the NMEA2000 Message Builder, where CAN messages can be created by entering the wanted signal value, i.e. water speed equals 10 meters a second, rather than translating hexadecimal byte values. X-Analyzer can send fast packet frames from the NMEA2000 protocol from the object transmitter, as well as receive and decode fast packet frames. There's built-in decoding of the NMEA2000 CAN message identifier, broken down into PGN, source address, priority, plus more. And then the professional version also comes with decoding for J1939 and CAN Open. Have a look at the feature comparison here. The next product we have is the newly released N2K Picoscope Kit. We shall talk later about network physical layer faults this kit will help to identify. However, it comes with the X-Analyzer 3 Picoscope only software, the hardware of the 2206B model Picoscope, the Picoscope 6 software, a dual BNC to M12 cable for connection, and a Warwick Control carry case. The idea of this kit is to give marine engineers the ability to check the NMEA2000 network's physical health, with the Picoscope feature displaying the network's physical messages in graphical waveform. So each device's electrical waveform is displayed to easily identify faulty devices, as well as help establish location of the network fault. The last product to introduce is the marine NMEA2000 Scope Kit. This is the top-end product, which includes the following: X-Analyzer 3 Professional software with NMEA2000 decoding, a Cavasa Leaf Lite V2 single CAN to USB interface used to simulate NMEA2000 devices, the Picoscope Model 2206B PC oscilloscope with scope probes, and comes with the Picoscope 6 software. M12 to D9 cable to interface from X-Analyzer to the NMEA2000 network, M12 to dual BNC cable to interface from the Picoscope to the NMEA2000 network, a Warwick control carry case, and then a USB stick with the relevant files and software. So this is the all singing, all dancing kit that gives the features including signal decoding from X-Analyzer 3 Professional, as well as the Picoscope layout for physical layer analysis, along with some handy connecting cables and a carry case. So everything needed for full NMEA2000 network analysis. So let's give an overview of NMEA2000 and CAN. This basic introduction will include a tutorial on how NMEA2000 uses CAN, and a tutorial on the CAN frame including the CAN ID, DLC and data segment, and also how this relates to NMEA2000. The first most relevant part of the CAN frame is the identifier. For NMEA2000, it uses the extended CAN identifier, which is 29 bits long. Within the identifier, you will have firstly the priority and data page regions that relate to NMEA2000, then the message PGN, which is technically made of two parts, the PDU format and PDU specific. The PDU specific is used with some PGNs to address the message to another device only. And then there is the source address at the end, which each device claims a separate source address when the network starts up. Next is the data length code, or DLC. This gives the length of the data segment that will follow. It is 8 bits long and has a range from 0 to 8. Now fast packet frames will decode as 8-byte CAN frames in the X-Analyzer raw trace. However, in the NMEA2000 layout, it will decode fast packet frames giving the above 8-byte DLC. For example, 26 bytes. But remember, it's the fast packet protocol that defines the fast packet frames, and CAN messages can never be above 8 bytes long. And finally, the data segment. This can be from 0 to 8 bytes long. Obviously, the fast packet exception was just explained, and holds the engineering data within the CAN frame, like speed water referenced, wind speed, and GPS location example of the NMEA2000 engineering signals. The engineering signals for NMEA2000 are defined within the standard. Here we shall show the wanted values for the NMEA2000 CAN message electrical waveform. As you can see from the diagram, when the CAN frame is dominant or logic 0, the CAN high voltage should be reading around 3.5 volt, and the CAN low voltage around 1.5 volt. The most important electrical quality of the CAN frame is the 2 volt differential voltage, to define the difference between dominant and recessive bits, or ones and zeros. So here's a look at the new N2K Picoscope Kit for electrical CAN waveform analysis. So now you have an overview of CAN and NMEA2000. Here are the faults it can identify. Here is an NMEA2000 CAN frame displayed on the X-Analyzer Picoscope feature. Here we can see the feature shows the CAN high voltage of around 3.5 volts and the CAN low voltage around 1.5 volts. Then the differential voltage shows around 2 volts. So a healthy CAN frame. Then the software breaks down the NMEA2000 CAN frame segments on the key at the side. Then we see at the top of the display, it shows the NMEA2000 CAN ID, which we shall explain later how to decode, and whether the frame has been decoded as okay. This is the feature we are releasing to marine engineers with the N2K Picoscope Kit. So let's see what faults can be identified with the kit. Next we see the fault CAN low shorted to ground, spotted with the X-Analyzer 3's Picoscope feature. As we can see here, the waveform has completely changed as CAN low is pulled to ground. The interesting part about this fault is because there is still a differential of around 2 volts, other NMEA devices and interfaces will still decode the frames. So without the Picoscope physical analysis, it could appear that the NMEA2000 CAN network is okay, when actually there's a CAN low to ground fault, and could be one wire break away from system failure. The NMEA2000 CAN bus should be terminated with two 120 ohm resistors at either end of the network, across the CAN high and CAN low signal wires. This can be checked with a multimeter across CAN high and CAN low and should read around 60 ohms, but obviously resistance checks should be done with the power isolated. To get an idea of how well the bus is terminated, you can look at the differential voltage of the NMEA2000 messages. Here we see a waveform with a differential voltage of about 1.7 volts. With this network, all the messages had a differential voltage significantly below 2 volts. This could indicate the network is over-terminated and can be checked with a multimeter when the network can be isolated from the power supply. Some marine installers who do not properly understand NMEA2000 have been known to add additional resistors. On the other hand, if the bus is under-terminated, you will get a differential voltage above the 2 volt region. As we see here, the differential was around 2.7 volts. Again, the same with the over-termination issue. All the waveforms on this network had a differential voltage significantly above the 2 volt range. So again, the resistance can be checked at a convenient time when the network power can be isolated. As said previously, the differential voltage is the most important electrical quality of the CAN waveform, and we have seen here how termination can alter that electrical quality and has the potential to affect NMEA2000 communication. Here we see a waveform that looks like the square wave also moves slightly like a sine wave or an ocean wave. This was due to an earthing issue with a singular device. All the other devices on the network showed to be healthy, apart from this one, which had an internal earth fault. Also, here we can see some ringing on a CAN waveform, which could become an issue over time, but again, just produced by a singular device. All of the waveforms on the network were healthy. Some NMEA2000 network faults will not be decoded by the X-Analyzer's Picoscope feature. However, if no valid or OK CAN frames show, you can then use the Picoscope 6 software to see if there's any electrical signals that are being produced on the NMEA2000 network. So X-Analyzer scans the network and grabs one example of each CAN ID waveform on that network, useful for whole system audits, whereas the Picoscope 6 software is useful for entire system failure. The X-Analyzer will not decode. When connecting using the Picoscope 6 software, if you see this when opening the Picoscope 6 program, and then this after loading the Picoscope 6 project, there is no NMEA2000 CAN devices communicating on the network at all. The other faults that only the Picoscope 6 software will show are CAN high shorted to ground, and the other fault is CAN high shorted to CAN low. Another method to understand what may be going on with the NMEA2000 network is completely the opposite. Inject a fault onto the network to understand if the network can recover from a physical fault or a bus off state. Movement of a vessel components could be causing intermittent faults that the bus or network may not be recovering from. So you can try these 3 fault situations: a CAN low shorted to ground, CAN high shorted to ground, and CAN high shorted to CAN low, and see if the bus or network recovers. Creating these faults could be done via a homemade fault box, easily constructed with an M12 connection, bare NMEA cable and switches, or we do provide a manufactured rugged fault board that can be purchased on request from sales@warwickcontrol.com. And here are the features of the board with the possible faults it can create. Obviously, it does the faults mentioned plus more. We've also produced a handy fault finding flowchart to give you direction of where to go with the hardware and the software. X-Analyzer's Picoscope feature will display the NMEA2000 message ID. The source address of the message, claimed by each device on the network, are the last 2 digits of the hexadecimal ID. If you work in decimal, the kit comes with a rugged conversion sheet from hexadecimal to decimal for the possible source addresses, and hexadecimal to decimal conversions for the PGNs in the message IDs, as well as a simplified way to understand how to read the message PGN from the ID. Here's the cheat sheet to pull out the PGN from the CAN ID, followed by the hexadecimal to decimal conversion sheets. So now let's move on to the benefits of troubleshooting the NMEA2000 CAN network with X-Analyzer, the CAN analysis software from Warwick Control Technologies using a Kavasa interface. Firstly, we have the statistics panel. This will give you general CAN stats about the NMEA2000 network, like the bus load. Networks optimally work for time-critical messages at 40% bus load and below. Non-time critical messages can have higher bus loads, but overloading the network can cause messages and their data to be missed. The panel also notes the max bus load seen during the analysis session. Then there's the error frame count. NMEA2000 CAN networks should not constantly be producing CAN error frames. Really, any error frame production on a network should be investigated. This stats panel gives an overall count as well as the transmitted and received error frames. The panel also shows the bus state that changes from uninitialized to initialized and then will change depending on error frame production on the network. The parts of the statistics panel most useful for troubleshooting are the areas just mentioned, but the panel also shows transmitted and received frame count overall, as well as transmitted and received frames per second, as well as any lost frames. This statistics panel is also available with the X-Analyzer 3 Eco software, which we give away free to anybody who has a Kavasa interface. X-Analyzer 3 can also transmit and receive NMEA2000 messages in single frame format and fast packet frame format. So NMEA2000 devices can be simulated using the object transmitter to send the frames. Let us run through constructing one in a video, firstly with the single frame. To create an NMEA2000 message, choose the Transmitter tab, then New Transmitter. Here we see construction of a single frame. As you can see, you construct the NMEA2000 message ID, DLC, and data, and then give a delay and auto repeat if the frame is cyclic. The transmitter can then be named and even given a shortcut to start and stop. Here we see an NMEA2000 fast packet frame, which is engine parameters dynamic. Create a transmitter as before, and then choosing the NMEA2000 transport as the transmitter type. Choose the frame type as fast packet, enter the priority and PGN, and then the fast packet DLC. Then enter the wanted data. Then a delay can be applied, and auto repeat if necessary, and then again the transmitter can be named and given a keyboard shortcut. Here are the 2 frames being transmitted via the F1 keyboard shortcut with the chronological view, seeing frames in the order they're received. Then the plus button drop down will show the NMEA2000 signal decoding, then we can choose the F1 shortcut to stop again. The new NMEA2000 message builder feature allows the entry of a signal value, i.e. water speed equals 10 meters a second, rather than converting hexadecimal byte values. So let's have a look. The single frame earlier was created using the message builder. Just add a row, select the row, and then choose build message. Then select the transmitter as NMEA2000 transport. Search for the message PGN with a find box. Select the wanted PGN for transmission, Here we chose speed water referenced, then enter the physical signal values, saving time using a programming calculator to convert 20 meters a second into the correctly scaled and offset hexadecimal value. Then press apply. Then enter the message priority and data page, set a delay if necessary, with auto repeat for cyclic messages, and then the message with the wanted signals is ready to send. The NMEA2000 decoding will also break down the parts of the message ID that we mentioned earlier. So let's see what you get. The NMEA2000 CAN message identifier is broken down through decoding into the source address. With the filtering feature as well, the display can be easily configured to show only a single source address or any combination of device source addresses you'd like to view, instead of monitoring the whole bus. Then there's the message PGN. The decoding gives the PGN name also, i.e. engine parameters dynamic, as well as the PGN value that can be useful when searching manuals and the standards to get where you want to be and find that nugget of technical information. Also use the hex to dex switch to view the different number formats. Then there's the message priority. Most NMEA2000 messages in practice keep the same message priority. However, it is part of the NMEA2000 standard that a message priority can be altered through the command group function PGN. So the decoding breaks down the identifier into a readable priority number. So again, there's no need to get the programming calculator out. The data page. You will see some PGNs in hexadecimal start with a 1, i.e. 1FD02, the win data PGN. The 1 at the start sets the data page to 1 instead of 0 within the bits of the message identifier. This is mainly for the development side of Xanalyzer, but there for marine engineers to view if necessary. Then there's protocol specific, PS. Again, more for the development side of work. This gives the part of the PGN that denotes the source address to which the NMEA2000 message is being addressed. So an ISO request with a PGN of EA03 is requesting information from the device with source address 03 only. This is possible with a certain range of PGN. Xanalyzer also comes with the same features as NMEA2000 but for J1939 and can open message ID decoding and network management transmitters for CAN open. Here's a quick look at both layouts. Firstly, the J1939 protocol decoding, showing the frames in order they're received with ID decoding and PGN name. The signals panel from the embedded J1939 signals, which the gauges and the scope work off as well. And then obviously the plus button drop down for the J1939 message, as well as the J1939 message builder. Then for the CAN open protocol, we have the network management transmitters to move CAN open devices through different states like operational to stop, with broadcast and addressed options. Here we see the network management messages, and then using the real-time playback, we can demonstrate the CAN open message ID decoding. You can also load CAN database files, DBCs, to use features like the scope, gauge, and signal panel to decode signals for that network. Now let's take a look at the NMEA2000 engineering signals decoding features, plus the added benefits Xanalyzer 3 has. Xanalyzer will display NMEA2000 messages in chronological order, i.e. one by one in the order they're received, as well as decode the NMEA2000 engineering signals and be able to display them with the plus button drop down, in a signals panel, and in gauges with the embedded NMEA2000 database, and then also within a scope, which can be exported. As well as exporting scope plots, log files of the NMEA2000 network can be recorded through saving through the raw trace and then played back via a virtual interface away from site. The licensing works in such a way that you can purchase one X-Analyzer Kavasa interface license. The Kavasa interface can be used on site to collect data, say with a technician. Then on another PC elsewhere in the world, you can review and analyze the NMEA2000 network log files on a virtual interface without the need for purchasing a separate license. Here's a little diagram. X-Analyzer 3 also has several filtering features. The filtering method can be used to isolate a source address on the display and only look at NMEA2000 messages from just that device. As you can see here, it uses logical operators and what you are or are not searching for to text filter the display to your wanted device monitoring. So thanks for taking the time to listen today. Please get in touch with sales@warwickcontrol.com for any questions you have. If you would like to trial the software, please head over to xanalyzer.co.uk and choose the Download X-Analyzer tab. Fill out the form and we'll usually have the evaluation out within the same day or the next day. And please don't forget to give your interface serial number for Kavasa or Picoscope. For Kavasa, they mark cert number or S/N, and the Picoscope serial number is in the format of star ET313-0021 *. If we've convinced you already, please head over to xanalyzer.co.uk/store, where the kits and the software can be purchased, or why not take a look at the cable section on the store for some handy connecting cables we have. Again, thank you for your time, engineers of the marine world, and have a great day.